Assalamualaikum. So today I'm going to explain a portion of this lecture which is under the oscilloscope part 2. So the focus for this lecture is basically on the oscilloscope probes. So for oscilloscope you cannot use this kind of cable because it is likely to pick up interference or noise. So they are not suitable for low level signals and they are also not suitable for high frequencies. Okay, so for oscilloscope they use a different kind of cables. So this cable can prevent unwanted signals being picked up by the oscilloscope input. Right, there are two types of probes. So the main focus is the passive oscilloscope probes. So there are two types. One is 1-to-1 ratio. So this 1-to-1 probe means that whatever the signal source is showing, that is what the oscilloscope is going to display. So it's 1-to-1 ratio. So that's what it means by the one-time scope probe. So this 1-to-1 scope probe is suitable for signals between 6 MHz to 10 MHz. Alright, so you can see here this is a signal source. So this is the cable capacitance, and then you have this oscilloscope input. So the oscilloscope input will have the CI and RI. Okay, so input capacitance and input resistance, and you will see these values in the front panel of your oscilloscope. Okay, now you can see here on the front panel here, right, the values of CI and RI. So it says here that RI is normally 1 megaohm and CI has a range between 15 to 30 picofarad. So picofarad is 10 to the power of minus 12, right? So however, for high frequency or high impedance signal, the 1-to-1 probe will cause this loading effect, which means that the output is no longer correct, and because of this you need to use a different kind of probe. So that probe is referred to as the 10-to-1 scope probe. Okay, so the 10 times scope probe is introduced in order to control the attenuation factor. So basically the output is not going to be the same as the input, but at least you know that it's going to be factorized by a factor of 10. So basically the 10-to-1 probe has this adjustable capacitor here in parallel with the 9 mega ohm resistor. Okay, and then this is the cable with the capacitance C2, and again this is the input resistance and input capacitance of your oscilloscope. Okay, so in order to obtain a properly compensated voltage divider, the time constant between the input network and the output network must be the same. Okay, so the time constant is equivalent to RC. Alright, so this is quite straightforward because you just multiply this value of C here with this resistor. Okay, however for this capacitance, so these two capacitors are in parallel, so what are you supposed to do with parallel capacitors? You are supposed to add. So that's how I get this value 20 plus 90 picofarad, and I multiply with 1 mega ohm. What I'm trying to show here is that we know these values, so we can calculate the time constant, right? But because this is adjustable, we have to calculate the time constant for this portion, and from there we can calculate C1 here, and it should be equivalent to 12.2 picofarad. Okay, so I hope you can follow what I'm trying to say. Basically this portion of your RC must be equivalent to this portion of your RC. Another way to find it is by using voltage divider. Okay, I think I missed this information in your slide, but the frequency used for this calculation is 20 MHz. Okay, so another way to do this is for you to calculate the reactance of the capacitor and then do this voltage divider formula. Okay, so this portion is your Z2 and this blue portion is your Z1. Okay, so V0 is measured across your Z1. Remember, you add this capacitance, so it's 110 picofarad, right? So when I calculate the reactance for that is this 72.34 ohm, and this reactance is in parallel with the 1 mega ohm, and that is how I get this value. Okay, so when the reactance of the 110 picofarad in parallel with the 1 mega ohm resistor, I will get this value. Okay, now the reactance for this capacitor here, which is 12.2 picofarad, is this value. Okay, right? and therefore this is the equivalent resistance. Okay, so when I do voltage divider to find V out, I get the ratio 1 to 10. So I have proved that the output will be factorized by a factor of 10, or basically what I'm trying to say is Z2 has to be 9 times larger than Z1. Okay, so this value, okay, has to be 9 times larger than Z1. So what I'm trying to show here is, let's say you do not know this value at first, but you are given the frequency. So you go ahead and calculate the reactance, and then you straight away multiply by 9 and you will get this value, right? So you can use this value to calculate the capacitor as well. So there are two ways for you to calculate the value of this capacitor, either by multiplying by 9 or by using the time constant. Depends on the information provided for you. Okay, so here in this slide, I would like to show you my PSpice simulation. Okay, so you are measuring a 1 volt input signal. Okay, however, as I mentioned, this value will be reduced by a factor of 10. So this is what I get at the oscilloscope input. So you can see it is reduced by a factor of 10. So I will see 100 millivolt. Okay, so take note that the scope's input capacitance C in, okay, must fall within the probe's compensation range. For example, this series of oscilloscope shows that at 1 mega ohm input, you need 13 picofarad of typical input capacitance. So based on this information, you need to use a scope that has 6 to 15 picofarad of compensation range. Okay, so in this example, the question asks, the input capacitance of an oscilloscope can be from 15 picofarad to 50 picofarad. So this is my range of input capacitance, and this is the cable capacitance. So now you are supposed to calculate the range of the adjustable capacitor. So the question gives you the hint, use time constant. So why don't you pause the video first and try this on your own using the time constant, and I will give you the answer later. So this is the TentoOne probe in the example. So you are given R1 equivalent to 9 mega ohm. The cable capacitance is 102 picofarad. The input resistance is 1 mega ohm. And the input capacitance has a range between 15 to 50 picofarad. So the question asks you, what is the range for the adjustable capacitor when you have this range for your C-in? The question asks you to use the time constant, which is RC. Okay, so you need to use RC. Right, so what you need to do is, you need to find RC for each condition. And because RC has to be the same for this combination and this combination, so you can find what is C1. So let's start with the first condition, when your C-in equivalent to 15 picofarad. Okay, so because there are two capacitors here, you have to add them up. So C total equivalent to 15 plus 102, which is 117 picofarad. Okay, so the RC for this combination is equivalent to 1 mega ohm multiplied with 117 picofarad, and you will get 0.117 millisecond, right? So this RC has to be equivalent to this RC combination. Okay, so I'm going to do it here, right? So 0.117 millisecond has to be equivalent to 9 mega multiplied with C1, right? So C1 equivalent to 0.117 millisecond divided by 9 mega ohm, you will get 13 picofarad. So now you get the first value of the range. 13 picofarad corresponds to the 15 picofarad. Okay? So now let's do the second condition. So for the second condition, now your C-in equivalent to 50 picofarad, which means that the C total will be 50 plus 102, you will get 152 picofarad. So similarly, you calculate your RC, which is 1 mega multiplied with 152 pico, and you will get 0.152 millisecond. Okay? So similarly, 0.152 millisecond equivalent to 9 mega multiplied with C1. So C1 equivalent to 16.9 picofarad. Right? So for this example, the range of C1 is from 13 to 16.9
picofarad. So this is your answer. Alright?
So this is a picture of an oscilloscope probe. So if you have the time to go to the lab, you can see that this is this adjustable switch here that you can switch between 1-to-1 or 10-to-1 probe settings, right? So let's do one more example here. Calculate the capacitance of the adjustable capacitor, alright, which is again, we want to find this capacitor. If the coaxial cable, this cable here is 106 picofarad, and you are given the reactance as 50 ohm, right? So this question did not give you what is the input capacitance, but it gives you the reactance value and the capacitance value of the cable. So what you need to do is you need to find out what is the frequency, and from the frequency you can calculate the capacitance here, because you are given the total impedance of this combination. 9 mega ohm is in parallel with this capacitance. So I will show you on how we can get this answer.
A few moments later.
So this is the figure for this example. So you are given the reactance for the capacitance of the cable, which is 50 ohm, and the capacitance is 106 picofarad. So I have mentioned that you need to calculate what is the frequency. So you can use the frequency to calculate what is C1. Okay, so let's find the frequency first. XCC is equivalent to 1 over 2 pi FCC. So F is equivalent to 1 over 2 pi 50 multiplied with 106 pico. Alright, so the frequency is 30 megahertz. Okay, so this total impedance here is actually equivalent to 9 mega ohm in parallel with the reactance for the adjustable capacitance. Okay, so one of the tip for resistance in parallel is that whenever a small value of resistor in parallel with the huge value of resistor, the answer is normally the value of the small resistor. Okay, so you can see here, you know the answer is 450 ohm. 9 mega ohm in parallel with XC1. So this value is small. So this value is very, very small compared to this 9 mega ohm. So I can safely say that XC1 is approximately equals to 450 ohm. So this will save you time. So I can use this value to find out what is the capacitance C1. Okay, so I'm going to wipe this portion off. So now you know that XC1 is equivalent to 450 ohm, which equivalent to 1 over 2 pi FC1. Okay, so C1 is equivalent to 1 over 2 pi. The frequency is 30 megahertz and the reactance is 450 ohm. So C1 is equivalent to 11.8 picofarad, which is the answer that I have shown you in the slide. Okay, so that's how you solve problems related to the 10-to-1 probe.
So actually, it is important that every probe be correctly adjusted when it is first connected for a use with a particular oscilloscope. So you can see here, if your square wave output have this shape, it means that the adjustable capacitor is too low, and if you see this shape, it means that it is too high. So this is how you can calibrate your oscilloscope probe, by observing the square waveform that is normally used in the oscilloscope. So earlier in the video, I've mentioned that there are two types of probes. So I have been explaining about the passive oscilloscope probes. And another one is the active oscilloscope probes, which are normally used for a higher range of frequency up to 2 gigahertz. So I'm not going to cover much about this, because the main focus of this lecture is the passive oscilloscope probes. So the assessment will be more on the passive probes. Okay, so in the next video, I will be showing some examples for the sensors. Right, I'll see you then. Assalamualaikum. Bye.